we can move on to the presentations. And I have a list here. And first up is May. And if you're ready to go and can share your screen and the technology actually works, is that okay?
Yeah, can you all hear me for now, at least? Okay,
Yes.
great. Let me see if I can share my screen. That should hopefully work. And then let me see. So all good. Can everyone see me?
That's
and
perfect.
See the screen?
Perfect.
Okay, perfect. So yeah, my name's May. And I focus my project on uncovering uncertainty in Alzheimer's disease biomarkers using automatic MRI segmentation, and Dr. Ivor Simpson was my supervisor. So a bit about the background. Alzheimer's disease is a type of neurodegenerative disease that causes dementia. And worldwide, it has caused an increase of deaths of Alzheimer's disease of 145% over the past 20 years. So it's starting to become a more and more pressing issue. And the key thing is that at the moment, there is no cure for Alzheimer's. So the best chance we have for improving the quality of life of people that live with Alzheimer's disease is if we can sort of enable an early detection of it. And that's quite difficult. And a source of hope at the moment is medical AI and using machine learning models for it. So that's what I was focusing on. So first of all, if you want to use medical AI for an early detection, you need some sort of way of collecting informative data about the person. So biomarkers are kind of like the type of data you want to be collecting. So biomarkers just are measurable and reproducible indicators sort of what's happening in your body, and you can compare them between different people and they will give you informative information about their state. And one way you can, for example, extract biomarkers from a person is through neuroimaging, and that's what I focused on. So neuroimaging, there are many different types of it, but specifically MRI was the one that I focused on. And the hippocampal volume, the left and right hippocampus, are strongly linked with Alzheimer's disease and cognitive decline. So what I did was that I used MRI scans to extract the hippocampal volume of different patients as a key Alzheimer's disease biomarker that can help with early detection. And one of the key sort of shortcomings of using MRI for this sort of data collection is that it's very time intensive and it involves a high manual cost, which is why I wanted to look more into using machine learning for it. So one way you can extract the hippocampal volume is through a segmentation of the MRI scans. So once you collected them, you can use a machine learning model to label the individual pixels in the MRI scan, which are also known as 3D pixels or voxels, and assign each of them sort of like a class label to which part of the brain or which anatomical structure they belong to. And you can use a machine learning model for that, which is then less time consuming and can actually help in early detection. However, there are some concerns of using machine learning for it. And the key factors are bias, variability, and uncertainty, which are often introduced through machine learning models, which can then sort of impact the reliability of using a machine learning model for segmentation and acquiring this informative data about a patient's state. So this is where my project aim came into sort of introduction, that I wanted to characterize the uncertainty that we introduce into neurodegenerative disease predictive models when we use MRI segmentation-based machine learning models, and find a way, once we characterize this uncertainty, to improve confidence in diagnosis and treatment effect. And the sub-aims were focused on finding a way of quantifying the variability that we find, and then seeing if the variability in, for example, the predictions of the machine learning model, if they can have any sort of effects on the confidence of a predictive model used for disease diagnosis or something in this direction. And the hypothesis that I had was that the uncertainty and variability that we get in the prediction of different machine learning models for segmentation are likely to increase as a patient progresses through the disease, as often there is less training data available in later disease stages. And also there's often like an increased structural heterogeneity in the MRI scans that need to be accounted for by the MRI segmentation model. So I'm not going to go through all of this, but this was sort of like a diagram I made about my project, where I started out with a data set of segmented and not segmented MRI scans yet. And for each patient, I ended up with a list of 4 segmentations of their MRI scans using different machine learning models. So I was sort of getting a set of plausible segmentations from different models, different pre-trained models. And I extracted the hippocampal volume from each of them. And then I wanted to see for each patient sort of if there is anything that we can learn about the variability from different models in a statistical modeling sense and predictive modeling sense. And over here is just one example. So these are the left and right hippocampal volumes extracted using pre-trained segmentation models for the same patient, actually, using 4 different models. And you can clearly see how different they look and how much bias and variability there is already introduced into the predictions that should be pretty much reliable and should be very reproducible across different models. But we can see how much variability there is, and this is going to later affect the diagnosis we're going to give to the patient. So a quick overview of my results and the analysis I had. So for the statistical modeling on the left-hand side, I had a gold standard segmentation mask. And to that one, I compared the segmentation masks of the hippocampal volume from different machine learning models and tried to see through the dissimilarity score, which compares the segmentation masks of the different models, if there's sort of like any pattern we can see. And we could actually see that, for example, on the left-hand side were the cognitively normal patients, then the middle ones were mild cognitive impairment, and on the right, the ones with progressed Alzheimer's disease. And for some of the models, there is actually sort of less agreement between the gold standard mask and the one it predicted for people like in progressed disease stages, which is obviously an issue since they are the ones most at risk. And then I also trained a variational autoencoder model in terms like the input data to that model was a set of the different hippocampal volumes from different machine learning models. And I sort of wanted to see how compressible the set of measurements is for each patient, and if there is any sort of pattern we can diagnose or like we can find in relation to their disease stage. And again, we could see that the model least confidently sort of encoded the set of measurements of the people with Alzheimer's disease and mild cognitive impairment. And the ones that sort of were only in the cognitively normal stage were the ones with the least variability in the measurements, which is therefore why the variance was the lowest of the variational autoencoder model. So that was sort of in line with the hypothesis I had in the beginning. And then what we can see is, again, that patients in progressed disease stages are the ones that are least confidently described by machine learning models, and the ones that suffer from the highest variability in their results using different machine learning models, different pre-trained ones. So sort of like the conclusion I've drawn from there that I want to investigate in future work is if we can actually use the subset of different biomarker measurements for the same patient and use it to counteract the individual bias from different model, and actually use it to capture the variability and see if it can tell us something useful about the patient. So just use a set of measurements that are all plausible to describe one patient. And that's sort of what I'm proposing in the extensions, that I could, for example, use either a confidence label to go with the biomarker, for example, the hippocampal volume, or you could, for example, use an encoded version of the different hippocampal volume measurements and use that to train disease predictive models for Alzheimer's disease. And one example that I gave was the PySustain predictive model software that could be used to try out this hypothesis for future work. Yeah. So that was a very quick run through of what I did over the year. I hope it's slightly makes sense.
Thank you, May. It was very impressive, despite being quick. I mean, I have to use chair's privilege and say, are you going to take the work further? Because it strikes me as very, very useful as well as very impressive.
I would love to take this work forward. Maybe not right now, but hopefully maybe in my master's, I can sort of connect back to that, kind of like build on what I've learned now and take that further. That would be great.
Well, yes, I think it should be taken further, but it's just a personal view. Charlotte asked a question about how did you get to do a project in the medical field? And I feel I should put Charlotte's question to you, since she is actually a member of our committee at Sussex BCS. But Norris has said you need to find a supervisor like Ivor Simpson. But would you like to say anything encouraging to Charlotte?
Yes, of course. So I kind of, I actually approached Ian about that a while ago, that I actually was interested in doing something in the medical AI direction. And he gave me some pointers about who to contact and sort of like in terms of staff who's interested in that, who does some research in this direction. And I got very lucky working together with Ivor on it, getting a lot of influence. And then I also selected a lot of neuroscience modules that were optional to sort of get that perspective as well.
Yes, and Norris has just typed, Ivor needs more final year project student supply. So
I'm sure Charlotte would be a great candidate for that.
Well, there's something good come up tonight, at least. Yes, thanks a lot, May. Rehan, are you ready to go and share screen and all that?
Yes, I'm ready. I'll share my screen right now.
Thanks.
Can everyone see my screen okay? And hear me as well?
I can hear you fine.
Perfect. So hi everyone, my name is Rehan Zuberi, and I was also supervised this year by Dr. Ivor Simpson, and I was lucky to do an interdisciplinary project also with Dr. Hilfred Hockeger. So he co-supervised this project, and he's from the life sciences department. So my project was building a unified machine learning model to perform multiple cell analysis tasks. So to explain my project aim, it all starts from the data, which is cell images, which are, we call them micrographs, as they were taken with a microscope of cells at frequent intervals to be able to see their evolution over time. But to be able to measure that, cell biologists usually segment each cell individually, either by hand or with some computer vision algorithms. And then from that, they're able to link them throughout the time lapse and see each time their evolution over time. And so we're able to measure, for example, the changing shape of the cell, maybe the changing marker expression, which is just different proteins they have, or even their cell division. And we're able to see how these cells change. One popular example is in cancer cells. If we see one cell dividing more than others and in a very rapid pace, then we're able to identify it as a cancer cell. So in my project results, I first had to segment and then to track the cells. And so I was able to report some good results, which was for the segmentation, a Dice coefficient of 0.98, which is out of 1. So it was, it proved that my idea was successful, the idea that came with my supervisors. And for the tracking, which is just the matching cells over time, I was able to get a 98%. So over the data we were working with, we got some very good results. So there was a good proof of concept on this project. So the question is, why would we want to do some cell analysis automation? So the first issue is that it's very long to do for cell biologists, as in to go hand by hand on thousands of cells, segment them out with their mouse, and then match them is a very, very long task. And they're often dealing with millions of cells. So it's not feasible. The second issue is that so they might go to algorithmic solutions, which are set in stone algorithms that usually work on a few data sets, but there's so many different data sets of cells that it's just also not feasible. And so then we go to machine learning solutions, which can give us some very impressive results. The problem with that is that when we're using machine learning, since we're dealing on data, we might feed the same data to different models. So we're going to give the same cell images to machine learning model that will segment, and then the same cell images to a machine learning model that will track. And so we might be collecting the same features. So the machine learning models might complete a lot of similar tasks. And since they're very computationally expensive, that will, first of all, take a lot of time. And second of all, use up more energy than needs to be. So that's the first intuition into why we would need to find a way to concatenate these two tasks into one single model to collect the features only once and then to complete two different tasks. So when we're using machine learning models, the first thing that happens in computer vision machine learning models is that we collect features on the images. So we're going to change our data to be able to find specific information about it that then we're going to be able to use. For example, a machine learning model in computer vision might find a way to increase the contrast between the background of the image and the actual cells. They will be able to find the cells and so then say, I found a cell over here, and then we get this information out. So as we can see, for example, here, so this is a nice image of cells, and we're able to see some marker expression from it. So the blue coming out, which is a bit more clear, a bit more white, are cells. And so this is the kind of data that will be transformed by the machine learning model to get this data out. So our solution was to think that the main idea behind this project is then if we build one model which can solve one of these tasks. So for example, if we build one model to segment the cells, then we can look at the features that this model collected and see if we can then interpret them to solve a second task. So first model solves segmentation, and then we use the features it collected to not have to use a second machine learning model, and we use these features then to track the cells and match them over time. So here's how our segmentation process would work. We would have first a cell microscopy image. Our machine learning model would collect features and transform the image to be able to make the cells stand out more. So as we can see on the second image, the cell probability prediction, we see the background is more bluish, and the cells would be a little more yellow or white, and so this contrast would be created, which would be increased compared to the original image. And then from there, we can just threshold and say, well, any pixel which is above this value will count it as our binary cell mask, and otherwise they're in the background. And then we just use another algorithm to separate out the cells individually into their own, just to show which each cell with its own unique mask. And as in computer vision, it's a lot of data manipulation. This is an example of the kind of data transformation we'll be doing, which are pre-processing steps where we're going to increase the size of the image. We'll split it into smaller crops, and these crops are then fed into our model, which is a unit machine learning model. I'll explain after how this model works. And then the output data, so it's not immediately our binary mask that we wish for. We first have to do some more transformation. So even if those features are collected, they still need to be interpreted either by algorithms and by our machine learning model. So this is the unit model architecture, and it has a very clear distinction on when it collects features and when it uses the features. And that's first, so on this line, the first line 120 by 128 is where we'll feed the first image to our model. And when we give this image, the model does an encoding step where it will downsize the image size, but it will increase the number of features. And as it's doing that, it's actually just collecting all these features that we have here, and then it decodes it to give us our binary mask. So when it encodes all these features, we can then use these features. These are the kind of features that we'll be then extracting, as it's this very rich information about the cells. It's these the salient features about them are extracted, and we can take them out and use them for tracking. So this is again, so then we have the cell microscopy image, we put it through a model, we get the cell probability, and then we're able then to do these post-processing steps through a second. So in our step, it was a little convoluted, but we had to use a second unit architecture. So we had this double unit architecture. So for our training data, what we used was model distillation, where we use CellPose, which is a model which already exists that does cell segmentation. And we tried to, since it's a very large and convoluted model, we tried to bring it down to a single unit, which would let us have this architecture that lets us extract the features out of it. And with those, that created then the training data that we would use to train our own model to make the binary mask predictions. So then we did, this is a little more technical and less useful to understand this idea, but we did some hyperparameter searching where when we're training some machine learning models, what we do a lot is we try to search for the right settings of this model to be able to reach a good end result. And so this is where maybe it's will be less energy efficient, as we may have to search through a lot of settings to get then to these results. So these are just example values we went through. And these are some of the example binary segmentations then that we can get out. As we can see, then we have this first image, and the cells aren't very clear, but our model is actually very good at getting some of the cells out. Sometimes the shapes are not exactly correct, but most of the cell was usually extracted. We usually get 0.98, and so this might be the kind of results that makes it that we're not 100% sure every time. It's that we get just the shape is not exact. So then this is then when we go from a binary mask to separate the cells into their own instance segmentations. So because we don't want to just have information about all the cells, we want to be able to show all individual cells, so then be able to track them. So we go through these computer vision steps. So this is also a step for us to use less machine learning and to use more algorithms that will consume less energy. So we'll just do some erosion and cluster finding, and then be able to label each pixel as belonging to a specific cell or belonging to the background. And then we can go on through actually tracking. So then for the tracking, we are using all the features we got into our units, and we're able to then give these results. So this is just the results we actually find is just to show we're able to give a unique number to each cell, and then to say, well, then this is cell 27, and this is cell 25, and cell 44, and so that they're tracked over time. So I think this is a better diagram to actually understand what a unit actually does, is that when we input our single image of cells here at the top left, each time it gives us, through the different convolution processes, it makes the image smaller, and it also multiplies the number of channels. So we can imagine as applying all these different filters to it, and so transforming the image in a way. And so when we finished encoding, so before getting to our binary mask and decoding, when we finished encoding, we get all of these features out. And so it's as if we had 64 copies of our initial image, but our machine learning model was trained to extract a lot of interesting features about them. So we have 64 different copies of unique descriptions of each of our cell that can be used for segmentation, but that then we can also use to segment out the cells and then use them to track them, as it's all these very salient features that are present in these channels. So then this is the kind of pipeline we would use, where we'd input our image of cell, we would do our pre-processing steps as described before. We put it only through the encoder, so not our entire unit, but only through our encoder. And then we're able to post-process it and get our 64 channels of output. And then this is the information that we'll use for the tracking. So for our matching method, what we use is then these representations of our cell, and we'd only use cosine similarity. So here, no machine learning models were used, whereas usually what you would find as a cell biologist is these machine learning models that would help you to track the cells. But here it was purely through algorithmic processes, so they're very computationally efficient. And they find just the cosine similarity between the channels, and that's what gives us good results. As if you have 64 copies of the same cell, it's very easy to know which cell is which, since you have so many features describing it. So then this is just the grid algorithm we use, but I'll skip over this. And so this is the end product, which is usually a nice one to look at, which is we can see the evolution of cells and their shape as they change. And so this is, since these are taking in a very small intervals, it's usually every 15 minutes, the cells may not change a lot. Here, for example, on match number 5, the cell only gets a little bigger. Or here, for example, here, this might be a little harder one that on a machine learning model, we would look for a very similar shape to this one, but here we have a much flatter cell than our original very circular one. So it's these it's this kind of more difficult situations we're trying to find to be able to show that our model does work well. And it's not just when the image does look very similar, it's able to find these, but even when the cell changes a lot, as it may go through division, or it may go through changing of expression, and these will be harder to match. So again, then we're able to see a sequence over a longer period of time, but it's a little less easy to see than the little differences. But here, for example, we can see the shape change a lot in the first line. So each line represents a sequence of matches, and so we're able to see that then the cell may change a lot, and our model was still robust in finding modifications. And so in terms of further work for this project, so we found that our results indicated that we could have compressed our models, use even more. I think that it was very convoluted, especially in the hyperparameter searching. And since we were using a double unit architecture, we could have used only one unit, but those results were found a little late. Secondly, that we are using 64 channels to describe our cells each time for the tracking methods, but actually we could have used only a subset of our encoding features, and we would have probably gotten a very similar results. And thirdly, that if we there are more tasks that we could solve using those features that they're so descriptive as we found, that we could probably be also use them for classification. So for example, for cells in their cell cycle phase, they could be classified maybe using these features as well. And so we'd be using only one machine learning model to solve 3 different tasks, and so being very computationally efficient. So that was my dissertation. Thank you very much for listening. And if anyone has any questions.
Thank you. I've got a question in the chat which says, what was the most difficult part of your project?
So I would have to answer this question in two, I think there were 2 parts that were very difficult in my project. The first one was in the hyperparameter searching. So it's interesting because Amey and Sergey, who are present here, actually saw me doing this. I had to train a lot of different models to be able to find the right hyperparameters that would make this model work. That is because the original model, which is able to segment cells very well, called CellPose, is a very large model, which is very computationally inefficient, but it learned very easily how to segment these cells. And since I was trying to extract the features, I used a much smaller model. So it's less lenient on letting you have some wrong settings. You have to have everything perfect for it. So that's what made it a very long and tiring process of and a very frustrating one of constantly just reading papers about which loss to use and which learning rate is best and which step. And so that was the first, I think, very difficult one. And secondly, I'd say it's in finding these kind of algorithms to segment the cells can also be difficult because it's a more fun process because it's iterative and it's you can see the results very quickly, but there's a lot more mathematics than you think in these algorithms that describe how to find the specific cells. So this is one of the algorithms I ended up using, but there were more complex ones such as Watershed, which tries to find the center of cells and kind of uses it in some ways simulates water to kind of label the pixels in a very iterative manner. And so that was also more difficult to implement. And often it felt like reinventing the wheel because you'd have to adapt it to your own data. So it's, it was still very fun, but it's true that there were some very frustrating and difficult parts to the project, but it was all worth it.
Thank you. Thank you. Philip, are you ready to go?
Yeah. Can anyone hear me?
I can hear you fine.
Okay.
I'm
going to share my screen.
Probably.
Yep. Okay, can everyone see my screen?
Yes, that's great.
Okay. So for my course, I studied games and multimedia environments. So for my thesis, I created a game. The game is called Lost Horizons, and it's a space-themed survivor game. And I think the best way to demonstrate what I created is a short demo of the game itself. So if I quickly play. This is the main menu. The player is able to create new game or load the game that they have created. There's different game modes, difficulty levels, where each difficulty has their separate the differences. For example, relaxed, there are no enemies which will attack you. You won't die, and the crafting and building is free, so that's also a part of the game feature. Each of these will vary. For the sake of the demo, I will just pick easy to show everything. And once you start the game, you'll be met with a tutorial of the game where it takes you through the basics of the game. For example, in the game, there's a bunch of items all over. You just go around and try to, the whole point of the game is to survive. You can also explore the whole world. As you can see, everything here, you can sort of float your way towards there. There's tools you can use and pick up, and you can equip them and also harvest items around the map. They will give you bonus items as well, which you can use to you can use it to craft other things to help you survive longer or better, easier, etc. You can also there's also vitals that you need to manage. For example, your oxygen level, your health level, water level, and food level. You can consume items to refill them and manage them like that. Oxygen will, right now I'm in a big oxygen bubble. You'll start to lose oxygen once you are, well, in space. Once you enter back in, yeah, oxygen goes back up. This kind of creates a challenge for the player to just try to fight against when they're really exploring the level. Around the level, there is a bunch of resources you can collect. For example, this thing, like scraps. There's also these voxels or marching cubes that are generated around the map, and you can harvest them with tools. They'll drop you resources, and you can use them to craft, you can use them to build, etc. If I quickly go here. There's these other ones where when you harvest them, they drop these raw materials. This is an iron ore, and you can refine them by just smacking again, and they just pop like popcorn, like that. You can also use these to craft whatever you want as well, and help you. Around the map, there's also a bunch of monuments for the players to find, and these monuments generally have things you can also collect to help, and tools and stuff. For example, this is a building gun. There's also building in the game where you can create like a house or whatever you want, just to store your things or have a safe space to stay in. There's also little bonuses or secrets around the map. For example, if I go here, there's like a pet you can tame. This little guy will just follow you around, kind of acts like a companion in space for you. He also holds some of your things just to help you get rid of things in your backpack if you are full. Yeah, as you can see, I've run out of oxygen, so I'm slowly dying, and you have to really manage that in the game. There's also enemies that try to just attack you, as you can see, like this. When you kill them, they kind of just disable themselves, and you can just harvest them for more extra resources. And when you die, you just get an option to respawn, which takes you back to the start. You don't lose your stuff. In other game modes, you do. Not the game modes, difficulties. So it depends on the player how comfortable you are playing the game, if you think you're good, you can go for a harder difficulty, which will make your experience a lot harder. The map is quite vast. There's a lot of structures for the player to discover and explore. So they have to try to find ways to travel there in a way, because the oxygen is limited. You can't really go anywhere you want, wherever you want. You have to find maybe, let's say, upgrades or build like a safe space for you to recover oxygen at. So yeah, I think there is also the main objective is to survive, but there is also a story element where you can, upon exploring, you'll find story items where at the very end, which is, quickly navigate there, it would be this building. So this is the, let's say, the final building of the final level of the game. If you make your way through here, these robots will just try to attack you, and you'd have to kill them, otherwise you'll die. I think if I just... So this will be the final area of the level. This is quite far from the start, so they'll have to obviously try get here without dying from space or enemies. The player has to find 3 objects to complete the game. These are scattered around the map. I can just give these to myself for now, just to speed up this demo. So if I pick these up, place them in, and then press this button, this activates just a cool little thing I added. So just to give the game purpose, I guess, in a way. And there's a little black hole here. Once you get close enough, you can kind of float your way in, and then the game ends there, like so. If I quickly go to this game mode where I can show the building mechanics a bit more, there's a complex system for building where I quickly give myself the building tool. You can build, so right now you're enclosed in an oxygen space. If you exit, you obviously lose oxygen because you're not in the oxygen space. You can create these modular buildings to kind of encase yourself from space. You can make them however big you want, however shaped you want, and as long as it's enclosed within, as long as you are enclosed within this structure that you build. So right now I'm enclosed. My oxygen has gone up, so I'm safe from space. I won't lose any oxygen or health. Once I exit, that will obviously drain down. You can build it however you want, and the algorithm for this was quite tricky to create because there was many like cases and edge cases to think about when doing this. So for example, if I enclose myself here, this is part of the same building. If I remove this wall here, I am now no longer safe because I'm exposed to space, but once I come back in, I am back to safety again. I think that is pretty much the main things of the game. Yep, that's my presentation. That's my dissertation.
Thanks a lot. You've got some fans in the chat and saying, "Have you published this so we can have a go?"
Oh, I haven't published this yet. I think there's plenty of room to improve and add. I wanna add a lot more things to this. For example, this building thing. Right now, if you're just enclosed in the space, you just get oxygen. I want to add maybe like a oxygen generation type of thing to make it much more harder to, because this is pretty easy. You just put yourself on a box. Like if I just do this and then just enclose myself. I'm pretty much safe and I can do that anywhere I want, which is kind of cheaty in a way. So yeah, I want to improve a lot more. There's even weapons you can, I want to, yeah, there's a lot more to add basically.
And one question in the chat: what were your biggest inspirations for your game, if any?
Sorry, I'm quite a big gamer myself, so I
Okay.
wanted to combine my passion because I really like space and I really like games, so I wanted to combine those two together, and I created a space survival game, and that because that kind of just motivated me to just go all out on this game, just to see what I can do, what I can really create with my passion. Yeah.
Thanks. Sophia, are you ready to present?
Yes, I'm ready.
Okay. Can you share your screen?
Yeah. Can everyone see my screen?
Yes, that's great.
Bit hard to follow after, but I'm Sophia. My dissertation was on customer relationship management with social media for fashion SMEs, which are small and medium enterprises. I study computer science for business and management. So my project centered around social CRM, which is a type of software that helps businesses maintain and nurture customer relationships through areas such as customer service, marketing, and sales. And the whole benefits that this type of software brings is better customer satisfaction, engagement, and support, returning customers, and loyalty. And I chose to focus my project on Instagram specifically because according to Instagram, 90% of users actually follow a business on the platform, and 2 in 3 people say Instagram facilitates brand interactions. My project focused mainly on a business called Vintage and Vintage in Brighton, and I decided to interview them because they were local, and so it was easy to go to the shop and actually speak to them in person. So my main scope of motivation, so I wanted to do research on social CRM and its features. I wanted to analyze some social media platforms and Instagram accounts to build a better strategy for the business. And I wanted to compare some social CRM software to find a specific software to recommend to the business. And these are all things that were part of my strategy that I created for the business. And it also included a business model that would, if you've never actually used a business model before, it explains how the business is going to use social CRM and how they're going to work once they've implemented it. And then finally, I wanted to evaluate the efficacy of my business model. And this is the canvas, the business model canvas that I base my business model on. So in my research, I did a literature review and I did some research on the customer perspective and the role that they actually have for a business. And I found that customers discover and advocate for small businesses on social media, and their feedback helps the business improve, and their content on social media can help mobilize other people to shop. Then I also found some goals and challenges that businesses struggle with, like gaining customer trust and loyalty, which can lead to competitive advantage, building brand reputation, and calculating indicators. Some of the barriers that I found to implementation were cost, time, knowledge, culture, and security. And to implement it in better ways, the research that I read recommended speedy responses and flexibility to changing business environments, which are actually an advantage that small businesses have because they are small, they're able to adapt quicker. Some of the benefits, as I said before, of social CRM are customer loyalty and retention, decreasing customer service costs, improving brand reputation and perception, and interacting with customers and building better relationships can also lead to better product development and conceptualization and creating better customer experiences in general. So the role of Instagram and social media are gathering customer information that can help businesses create better strategies, interacting with customers to gain feedback and create better experiences. And Instagram specifically can facilitate sales conversation and accepting orders through Instagram DMs and messaging, but also displaying products and making customers aware of the products and the services that businesses sell. And some of the focus areas that I focused on were customer service, which included messaging customers, feedback, and loyalty. And then with marketing, it was planning and creating content that is posted on social media, gathering analytics from content, and creating a brand presence. And finally, the third area was sales, which can create better leads and finding who to sell to, better experiences for customers, and efficiency. So for my overall methodology, I did a social media platform evaluation. I looked at 4 different platforms and I decided that I wanted to work with Instagram. So then I did some research on what are some of the shop features that Instagram offers for businesses. Then I evaluated some Instagram accounts to see what they do that makes them stand out in their area and their space, and how I could recommend this to my business. And then finally, I also analyzed some software and decided on which software I wanted to recommend. So for my data collection, I interviewed Caroline Noble from Vintage and Vintage. I asked her some questions about her general business strategy and how she would implement social CRM and whether she does, which she actually does not. So it was perfect for my project. I gathered some data and I analyzed her Instagram account to see what I thought could be improved. For my analysis, I created a strategy that had 4 areas: the business model, which you can see a skeleton of on the slide right now. I made some other recommendations in terms of like business strategy. I made a recommendation for the software, and I made an Instagram strategy on how to post and what to post. The business model that you can see here has a few explanations, but something that I want to highlight is some of those headings like value propositions, which looks at what value the business brings to their customers. And with vintage businesses, a lot of this value is offering items that are rare or not sold anymore, or just original and special. And the business model also looked at the key activities that they do and their key resources, but also at how they, like what their relationships with customers are like and who they are actually selling to, who are their customers. And then after doing this, I had a second interview with them, and where we looked at the efficacy of the strategy that I had made, and I gathered some improvements. For my improved strategy, I made some changes like adding more definitions and explanations. I added some key performance indicators, which they were supposed to be some sort of target to aim for once social CRM has been implemented. And for the recommended software, I added some explanations about why I chose the software and not just some of its features, and some customer success stories. In the other recommendations, I included recommendations on all of the different areas that I spoke about earlier. And I also improved the Instagram strategy a little bit. And then after improving and creating the business model, I spoke to Caroline and we looked at like how effective she thought it was. So Overall, she thought the strategy was very viable, helpful, and easy to understand. And the Instagram strategy was actually her favorite section because it was an area that she had only recently gotten into. She did have some minor adjustments, which I did make, but personally, I felt that the project was successful because it covered all of the requirements and specifications that I set for myself. I did run into some issues, like creating the key performance indicators was a bit tricky because Caroline herself doesn't actually measure them on a day-to-day basis, but I ended up informing them with my own research. Evaluating the software was a bit tricky because I didn't have access to it because it is paid software, but I looked at some of the websites and the kind of information that they give out in public. And some of the success stories weren't what I was exactly looking for. They focused mostly on feedback from the customer, whereas I wanted something a bit more like analytical and some more data, as in like the brand talking about how profit was affected once using the software. Thank you very much for listening.
Thank you. There's a question in the chat. If you were going to take this further, what would you do? But actually, can I put a question in before then, which is, was there any particular reason why you decided you wanted to work with Instagram rather than the other 3 social media platforms you looked at?
So Instagram, I felt, had some of the best business features, but
Okay.
the platform on Instagram is very popular for small businesses to sell on because it does have pictures, but it does also have video. So I felt it had the most features of a social media platform, but also had the audience that I was trying to target, I guess.
Okay. Well, like I say, there's a question here. If you were going to take this further, what would you do?
So if I were to take it further, I would have wanted to also interview a business that actually has already implemented social CRM and see how I could improve it, but also maybe look at some different industries and not just fashion.
Good. And someone's asked, was the business, this business already using some of the features on the platforms that you presented to them?
Yeah, so let me see if I can go back here.
Yeah, vintage and vintage.
Here we go. Yeah, so if you've heard of Square, those are the small white card readers that you pay with. Sometimes they collect some sort of data about customers. So for the most part, that covered the customer service and sales parts of the strategy that I was focusing on. And then I also recommended this Zoho Social, which focused a lot more on marketing. I did try to find a software that included all 3 of those, but it was very expensive, and I wanted to recommend a software that had a budget that was realistic for the business that I chose.
Good. Well, thank you. Sergey, are you ready to talk?
Yep, just let me share my screen real quick. Can everyone see the presentation now?
Yes,
Okay, cool.
that's great.
So, hi everyone, my name is Sergey. I did a computer science and AI course, and my project's called Self-Supervised Machine Learning on Brain MRI Data. I also worked with Dr. Ivor Simpson. And I'll probably start by giving a very brief description of what self-supervised machine learning is and what supervised machine learning is and what's the key difference between 2 approaches. So supervised machine learning is basically a learning paradigm type of machine learning where we have a model and a data set which is labeled by someone. And it means that every example in the data set is some piece of data, and also there is some label that the model can learn from. In contrast, self-supervised learning paradigm is a bit different because rather than having labeled data, we just have a bunch of unlabeled data. And basically, we were trying to predict parts of that input data from the same input data. So the supervised approach had a tremendous success until recent, and like a lot of big advancements in machine learning and AI where in this supervised learning paradigm. However, yeah, the main point is that it relies on huge amount of labeled data, which has to be manually labeled by humans. So, and since we live in the era of big amounts of data, we probably would like to utilize this data somehow without manually labeling it. And specifically in the medical domain, we have lots of data obtained, like acquired every day from patients, such as images or some measurements, and usually they come without specific annotations. So it's not just we want to be able to avoid manually labeling huge amounts of patients' data. We also want to make computers be able to reason similarly to how human experts do, and to make decisions like medical practitioners do. And like, you might disagree, but the supervised paradigm is unlikely to be the optimal way to achieve this. So for example, in the lesion segmentation task, which is a crucial task in a variety of clinical applications, typically it is performed manually and is reliant on comprehensive understanding of human anatomy. It's also quite time consuming. This is just the, one of the possible variations of lesion segmentation task, where we have brain images and corresponding masks. And this mask, they were acquired, they were basically manually labeled by medical experts, by several medical experts actually, which is indeed time consuming. So the main idea of my project was to implement several self-supervised learning models, and to be able to achieve similar results to supervised algorithms, but without using any supervision. So on this figure, you can see that there was a model in the center of all that stuff, and it was trained on healthy images only. So the green arrows, the green path here represents the training process. So during the training process, we've had the healthy data into the model and trained it to reconstruct this healthy data and probably to learn something about the data. And then during the inference step, we can pass the anomalous image to the model. And since the model hasn't seen this tumorous region here, so basically something that has never faced, it will probably reconstruct it as if it is normal, as if it is something it has seen before. So here you can see there is an anomalous image and a reconstructed anomalous image. And the reconstructed one, it sort of has like a normal pixel intensities within this tumor region. And we can then compute the difference between the two, also called the residual. It's like basically the absolute difference between the intensities of two images, and get some sort of prediction from it. So you can see on the residual here that the anomalous region is it has a higher intensity. We can then apply some computer vision basic morphological operations and probably extract that anomaly from it. So I've applied several machine learning models. The simplest one probably is the autoencoder. The main idea here is basically to compress the data to some low dimensional representation, to this low dimensional manifold, and then to reconstruct it. The main components of autoencoder are encoder and decoder, and both of them are just deep neural networks. There's also a generative variation of it, more like probabilistic variation of it, which is called a variational autoencoder. In this case, we have a generative model, so the idea is mainly the same as for the normal autoencoder, but rather we want to model the distribution of the latent features. Latent features are something that we don't see in the image, but it is present in the image. It might not just be visible for a human eye. So what we can do is to model the distribution, and then we can sample from this distribution and generate new images. So yeah, we have generative model in this case. Although in this project, I wasn't really exploring the generative capabilities, but rather how good the model can reconstruct stuff. But yeah, in general, once the model is trained, you can just sample from it and get a new healthy brain image, which is quite cool. And there were a few variations of it, basically extensions of these autoencoder models, such as vector quantized variational autoencoder. It's just basically the same thing, but it's like it has several additional components. It is discrete rather than continuous. but yeah, otherwise it's more or less the same. And also I use a combination of this model with the transformer model. I'm pretty sure most of you heard about transformers before. They're quite popular now with all the language models. Yeah, so I've employed several architectures to get the results. And there were also several data sets. So the original data set is called ICSI dataset, contains around 600 MRI scans from healthy subjects. And the scans were collected in 3 different medical facilities in London. So they come just as normal MRI volumes. So one of the biggest challenges was probably to pre-process those volumes so that my model can basically work on them. And the first thing I did was to remove skull from these volumes, which I did using another deep neural network, a pre-trained one. And once I've extracted the brain tissue from each image, I had to also transform the image because like when we take an MRI scan of a person, the person might be moving within a scanner. So the images, the volumes are very different from each other for different subjects. And also if we have several data sets, different neurologists, like different radiologists may sort of align them to different space coordinates, which also overcomplicates it a lot. So I needed for each volume to sort of register it, to transform it, to align it to a certain template. Also, I normalized each of those volumes and sliced them into 2D slices to make all the process less computationally expensive. So rather than working with 3D volumes, the model had to process 2D slices, which is actually easier because, yeah, it basically doesn't require that many parameters for a deep neural network. So, and this was the healthy data set I was using. I also used a part of this data set to synthesize anomalies so that I can basically test my model if it does work actually on something at the end. So yeah, and there was a part of this data set which was utilized for further testing. And there was also another data set called BRADS20, which is a data set containing the MRI scans of subjects with actual brain tumors. So in this case, there are different variations of glioblastoma. The reason I was utilizing this one is to basically test how the model could work in clinical conditions. So is it capable of generalizing to some sort of different data it has never seen before? Yeah, this was the second data set I tested it on. And there was also some post-processing pipeline. So basically once we get a prediction from a deep neural network, to transform this prediction into something reasonable to see the actual predicted tumor. So here on this image, you can see that we have an original image, then we acquire its reconstruction from the deep neural network. We compute the difference between the two, and then we apply some very simple binary operations to get the refined mask of that tumor. These are some of the results I got at the end. So the picture on the left are the results for the synthesized images. The top row are the actual images with synthesized tumors. The second row are the residuals, basically what we get from between the prediction of the model and the actual image. And then the third row are the tumor regions I've extracted using post-processing. And the final row are the ground truth tumor regions. So yeah, it's quite easy to sort of discuss all the stuff in terms of the data set it has mainly been trained on. So we'll move to the picture on the right probably, which is the data set it hasn't been trained on, which is a BRADS data set with actual tumor regions. So in this case, we can see that the third row, which is the actual predictions of the model, is quite close to the ground truth tumor segmentation masks. It obviously has some false positives and false negatives, but it is indeed quite close. It's localized well. So this allows to make some assumptions about the nature of those models and that they can actually be used for these sorts of tasks. On this image, yeah, and since I used like five different models, On this image, you can see 5 different MRI scans, the ground truth masks, and the prediction from each of the models. It ended up with a variational autoencoder being the best one in most of the cases. But there are also some assumptions that could be made about other models, and specifically the parameters, the configurations of those models. So a very important parameter of these generative variational autoencoders is the latent space size. And from all of my experience, I determined that lower dimensional latent spaces actually behave better and produce better results than high dimensional ones, which is quite interesting. I also did some statistical analysis on this, basically compared all those models. And again, in all of the cases, variational autoencoder, the simplest one, proved to be the most optimal solution. And some other figures from the statistical analysis part. And that's mainly it. Yeah.
Thank you. Interesting question in the chat. Did you have to learn new skills?
I obviously did quite a lot. I mean, apart from all the deep learning stuff, which I was sort of familiar with before, but I also learned a lot of new things. I also was exposed to working with neuroimaging software, which was something completely new to me, such as the software I used is called FreeSurfer. But yeah, there's a variety of other tools I'd like to learn probably eventually. Learn this, some basics of neuroimaging maybe, since this is sort of a domain I'm interested in. Also considering it quite useful. I would say I learned a lot. Yeah.
Thank you. Another one here. Would you say your project approaches or reaches state-of-the-art results?
It does for some of them. For some of the paper, it indeed does outperform. So the results are slightly better. But it's still, so it's not a novel idea. It's not something I came up with, but it's quite close to state-of-the-art. And yeah, for some of the relatively recent papers, it's even better.
Okay, can I say thanks to all the panelists, and by way of thanks, also mention that the meeting next week, BCS Sussex branch next week, will be a hybrid meeting, and it'll be a student-led meeting where you will get a chance to suggest what BCS could do for you. So it'll be in the Chichester Lecture Theatre and online, like this one. And the idea is that we'll get some suggestions from students as to how we could help you. Again, 7:30 next Wednesday, the 19th. Unless anybody's got any more questions, I think it just remains to me to say very well done. And please use your BCS membership, or at least tell someone who's likely to be at the meeting what BCS can do to help you. And I must say, I have been very impressed by the projects. I think they richly deserve awards. So well done. Thanks to everyone. Thank you. Well, I can do a.
Can I just add very quickly, Blay, just to thank all the speakers for producing, well, basically to say well done for producing such outstanding projects. There was probably another 10 projects that could have won this. It was a very difficult decision to pick the five winners. But congratulations to you all. It's really great to see these projects presented, and I hope you all go on to do great things building on these pieces of work. So well done.